This brings us to the most important topic of the day, projectile motion. This describes the motion of any object that is thrown or launched into the air and moves only under the influence of gravity, like the skater in this image. In this old school jump over an obstacle, the skater goes over while the board keeps going under the bar. This case study is a great way to begin. We can see the one-dimensional motion of the skateboard, reminding us of chapter 2 we just learned. The skater is traveling in 2 dimensions, and this multiple dimension motion is what our current chapter is all about. Let's consider this. If a skater is rolling at a constant speed and wants to jump up and land back to the board, how should they jump? Should they jump forward or straight up? This question leads to a very crucial concept in physics. So let's consider this scenario. If you are playing tennis on the deck of a huge cruise ship traveling forward, you can hit the ball straight up off your racket and it returns back to your racket. You don't need to consider the speed or direction of the ship. We can model this with a card that has a ball launcher. If the card is moving, what angle should we set to have the ball land back in the card? If the card isn't moving, we obviously launch it straight up. But what if it is moving? Should we angle the card forward in order for the ball to come back to the card? The answer, which might be surprising, is that you still need to launch the ball straight up. As this diagram shows, if you launch it straight up from a moving card, it will land back in the card. If you launch it forward, it will fly out in front of the card. This is because the ball, once launched, retains the horizontal velocity it had from the card. Its horizontal motion and its vertical motion are completely independent of each other. This is the single most important principle for understanding projectile motion. In projectile motion, horizontal and vertical motion are independent. The x component of velocity remains constant. The y component of velocity is 0 at the peak of the path. So the ball has only x component of the velocity at the highest point. This means we can use our simple kinematic equations that we learned in one dimension, apply them separately for x direction and the y direction, or we can call it the horizontal direction or vertical direction. The horizontal motion is just the displacement equal velocity times time for projectile motion because the motion is constant velocity in the x direction. The vertical motion is constant acceleration motion with the acceleration being g pointing in the downward direction. The time of flight is a variable that links the two motions together. This figure shows an experiment illustrating the independence of horizontal and vertical motion. The gun is aimed directly at the target ball and fired at the instant the target is released. In the absence of gravity, the projectile would hit the target. Because the target wouldn't move, however, the projectile still hits the target in the presence of gravity. That means the projectile is falling through the same vertical displacement as the target, despite its horizontal motion. Even if we adjust the target to be at an angle, this experiment also works. In general, our equation of constant acceleration follow separately for both the x direction and the y direction. Notice that the initial velocity has two components. Let's assume that at t equals 0, the projectile leaves the origin with an initial velocity v0 in this direction. If the velocity vector making angle theta 0 with the horizontal, where theta 0 is called the projection angle, then from the definition of the cosine and the sine function and the figure show, we can find out the x component of velocity should be given by v0, cosine theta 0, and the y component of the initial velocity should be given by v0 sine theta 0. And vx over time should be a constant because there is no force in the horizontal direction, no change of velocity in the x direction. However, v0, vy should follow constant acceleration motion, and our acceleration is negative g. This is our acceleration in the y direction. So we should just apply our kinematic equation separately in the x direction and the y direction and solve it. In the x direction, as we said, there is no force, no change of velocity. So velocity in the x direction should remain a constant and equal to the initial velocity in x direction. And the equation of motion is simple, just the displacement equals velocity times time. However, in the y direction, we need to apply the kinematic equation for constant acceleration we learned. Replace all the acceleration in y direction with minus g. Let's summarize these important facts about the projectile motion. 1. If air resistance is neglected, the horizontal component of the velocity, Vx, remain constant because there is no horizontal component of acceleration. 2. The vertical component of the acceleration is equal to the free fall acceleration, g, and pointing in the downward direction. The vertical component of the velocity and the displacement in the y direction are identical to those of a free fall body. 4. Projectile motion can be described as a superposition of two independent motion in the x and the y directions.